Okay, so to summarize first what we discussed till now regarding the Dirac equation. So our main motivation was to try to understand the motion of or the to understand the dynamics of, let's consider charged particle like electrons or basically the fermions, which is like in the domain of relativistic quantum mechanics. So where the quantum mechanics and relativity both in our picture. So we started with the Klein-Gordon equation, which able to give a kind of picture for this relativistic domain. Then what we found,
And the primary reason for having a Dirac equation is to solve two things. One thing is like we want to solve the negative energy problem which arises in the Klein-Gordon equation, and then the probability density was negative when you did the Klein-Gordon equation. So that was the primary reason. But at the end of the Dirac equation, what we are able to see is like the probability density became positive, but energy is still negative. Then we had like a discussion about like what about the negative energies, like what can we say about negative energies. Then we said like negative energies are something like those energy levels are already filled, so in a normal state. So that's how we stopped it.
yeah. So yeah, exactly. So the two important thing which was raised when we try to discuss about the Klein-Gordon equation. One thing was, as you said, the negative energy one, and the second thing was the probability density, which was negative. So Dirac tried to deal with this problem straightforward. So he demanded that, okay, we need an equation where the probability density it will be positive by default, by definition. So to do that, what he did, he start to factorize. So he tried first try to understand what are the source of this inconsistent or something which is unexpected. Unexpected in the sense like probability density is supposed to be positive. And then when he tried to tackle this problem, he found out, okay, the main source of this negative probability density in Klein-Gordon equation was this time derivative, the second order partial time derivative. And because that was the reason, or that was basically main source to get this negative probability density. And also the negative energy, because this is how the Klein-Gordon equation was defined. So the negative energy came by default. So to tackle this problem, one of the first approach that, okay, whatever the equation it will be in terms of relativistic domain, the first order time derivative, the partial time derivative, it should be linear in the equation of motion. That will ensure that the probability density it will be positive, because that was the main source of the negative probability density in Klein-Gordon equation. And to do that, also he need to keep in mind also the covariance form, because in relativity, the equation of motion that's supposed to be covariant. That means if you make a Lorentz transformation, if you go from one frame to another frame, if you see either this field is changed with respect to the change of the coordinate system, but this equation of motion, this is supposed to be covariant under Lorentz transformation. So to do that, he also postulate that whatever the equation, in the equation of motion, the spatial derivative, the partial derivative with respect to space, that also will linear in time. So to keep these two things in mind, he postulated the Dirac equation, where he found out, so the time derivative, the partial derivative with respect to time, this is linear in the equation of motion, and also the spatial derivative that also linear in equation of motion. So these two are things which is coming from the intuition of Dirac, what he actually trying to postulate. And then we also discussed in the last class what is the relation of alpha and beta. This is a two Dirac matrix we introduced in the last class, which is somehow interconnected with the gamma matrix. So here, all this alpha, beta, gamma, there is a special algebra. It's called Clifford algebra. I can write down. So this is a kind of a special algebra when we consider the space-time, the four-dimensional space-time. So all the spinor and the corresponding matrix, they're supposed to follow this Clifford algebra.
Okay. So one question I had, like when I was going through this slide, this equation I dou psi by dou t is equal to minus I alpha delta plus beta m. So that equation, right? I understand why Dirac wanted that form, but yeah, like we derived the Schrodinger equation from like E is equal to p square by 2m, right?
Mm-hmm.
So is it like he derived this equation from something simple, or he just said like, okay, this is what I want, and I'm going to find alpha and beta? It's like is there any basis like just like Schrodinger equation has E is equal p square by 2m? Does it have anything like this?
Into this equation, it is something like eigenvalue equation or H psi equals to E psi, but in 4 dimensions. So
Okay.
whatever the Hamiltonian is written here, the Hamilton, so this part, this r minus I alpha dot delta plus beta n, this is kind of like Hamiltonian of the given system, like whatever you also know in Schrodinger equation.
Yeah.
And also this mass
Okay.
term, so this is also kind of like kinetic energy plus potential energy term, not really, but it's in the relativistic domain. So it's kind of look like the Hamiltonian, the kinetic energy and potential energy. But what is
Okay.
important here, so when he tried to develop so this is completely postulate. Postulate means he knows what was the problem. So based on that problem, he tried
Yeah.
to try to get a solution.
Gotcha.
And
Gotcha.
so to develop this solution, so few things he was keeping in mind that okay, the Klein-Gordon equation, it was well enough. So but he knew what is the problem and he knew what is the source of the problem. So when he start to postulate, so he need a kind of equation like H psi equals to E psi, this energy eigenvalue equation. So it is exactly look like this. So this is your kind of energy representation. You can think like this. This is identity. So in operator form, it is kind of like energy, and this is the Hamiltonian. So
Gotcha.
it is quite look like Hamiltonian Schrodinger equation of motion. But what is a new thing here when you try to develop this theory
X
that
comma T.
yeah, so it's supposed to be like in 4 dimension. Like Schrodinger equation is not deal with the
Dimension.
relativistic quantum mechanics. This is completely non-relativistic one. So he wanted to develop a theory which will be well enough to understand the dynamics of some particle, microscopic particle. So it is in the quantum mechanics, which having this relativistic energy momentum relationship, like this energy momentum relationship, and the probability density will be positive. So he need this time derivative in linear form, and also he wanted, because it was just known that under Lorentz transformation the system should be covariant. So he wanted equation of motion in the covariance form.
Hmm.
So that's why he also, so this is complete intuition. So he,
Intuition.
based on
Yeah.
the
Yeah. That's what I was
intuition, he
looking for.
tried to develop this theory. And now the
Gotcha.
question was that why, from where this alpha and beta came into picture, because he needs some of the coefficient like alpha and beta that will be completely follow the four dynamics for space and time, and an obvious choice for him to construct some of the metric which will be follow this four-dimensional algebra, which is basically the thing what is come from the Clifford algebra. So which will be make ensure you that this alpha and beta are not random. Initially, it was just to consider this matrix because this space derivative with respect to
Go
x,
by
y,
dou X.
and
Yeah.
z, and then
Yeah.
whatever the phi, this phi will be like a four-dimensional kind of spinor state or
Yeah.
or spinor field. So he needs some of the matrix which will be satisfy all these possible conditions. So initially he just considered this alpha and beta, and based on he just follow his intuition. He already knew what was already known from the Pauli spin matrix. So
Gotcha.
he took, because this Pauli spin matrix, it also at some point follow all this Clifford algebra.
Gotcha. So
So
that is what I was looking for. So yeah, it is started with the intuition, but not too far from what we know, which is Hamiltonian H of phi is equal to E of
mhm,
phi.
mhm.
E of phi is equal to H of phi. Hamiltonian operator is equal to energy. Yeah, sorry. E of phi is equal to H of phi is equal to E of phi. One question I had was like the energy operator. Energy operator is given by I dou by dou t.
Yes, in the previous
And
slide, right?
momentum operator is given by minus IH dou by dou x. Right. So my question was like, why energy is in like time domain and the momentum is in position domain? I was trying to get like how do we get? I understand like once we apply it, we get it, but how do we get this momentum operator in the time in space domain and energy operator in time domain?
So this is also coming from the conservation law. Like if you remember, once we was trying to discuss about the Noether's theorem and kind of
Okay.
conservation law. So when you have a time symmetry, then the corresponding conserved quantity will be coming from the momentum. It's coming from the energy. When you have a space symmetry, the corresponding conserved quantity coming from the momentum. So this concept of conservation, I mean, this is kind of nature. This comes from nature. When you had a symmetry with respect to time, then the conserved quantity will be your energy. When you had
Yeah,
a symmetry with respect to space, automatically the by default conservation will become to the momentum. So
got it.
so that basically one-to-one correspondent, that your energy and momentum, these two are interconnected.
Okay, it came from conservation law. Okay.
And we try to understand set of relation between alpha and beta, and it is completely based on the Dirac postulate. What was the postulate here? When Dirac was trying to develop this theory, at some point he was agreed that whatever the wave function he defined also in his theory, this should be satisfy the Klein-Gordon equation.
Yeah.
And based on that assumption, if we can find out what is the relation based of alpha and beta, so there is an anti-commutation relation between alpha beta and alpha I and alpha j, I mean a component of alpha I and j. And also we find out what is the alpha square and beta square. So this is kind of like a given tool for us to play with this alpha beta matrix or the Dirac matrix, whatever he used in his equation when he tried to postulate this Dirac equation.
Yeah.
And then we play a little bit about this alpha and beta, and also I mentioned in the last class this alpha and beta. When we try to choose this alpha and beta, we need to keep a lot of things in mind, because this possibility to get this anti-commutation relation, which we get from Dirac equation, so we cannot choose any possible definition of alpha and beta. This alpha and beta should be unique. And if we try to understand how this alpha and beta transform under different transformation, then we always need to keep in mind that this commutation relation between alpha and beta should be preserved under any kind of transformation, whatever we can think of.
Yeah.
And to do a mathematical representation of this transformation, if we consider arbitrary rotation or any kind of arbitrary transformation, so we can represent this transformation using a matrix, and this matrix should be unitary. And that will be ensure us that the anti-commutation relation of alpha and beta should be preserved, which is kind of like by default definition we can get from Dirac equation. So in the last class also, we tried to dive more into deeply to understand what is the possible solution when I considered the Dirac equation as a solution. Then we start with the possible definition. So we can define the phi, which is a possible solution, which could be a possible solution for the Dirac equation. We can factorize this in two parts. One of the part which will represent the four component spinor or the bispinor. Again, this whatever the omega I define here, this will be all this, the corresponding algebra is Clifford's algebra. And also there will be a part which basically represent the plane wave solution and how the energy and momentum that is changed with when the particle had some specific dynamics in the space-time. So this part will be represented as a plane wave solution, and this part, this omega part, will represent the corresponding four component to the Dirac spinor.
Okay.
Then doing some more mathematical calculation, we're trying to reach at a particular conclusion that what will be the possible energy we can get from the Dirac equation also. And then we found out that possible energy, because as we already defined that what are the wave function of Dirac equation that also follow the Klein-Gordon equation, the possibility to get the negative energy was not nullified. It was still there because it was come by definition again from the Klein-Gordon equation. So the possibility of positive energy and negative energy, these two are still remain when we try to get the solution of a Dirac equation for a free particle.
Mm.
So when I mention free particle, I mean there is no additional perturbation, additional potential which will affect the motion of this particle.
Yeah.
And then we also try to understand, okay, energy is still negative. Then what is the possibility to get this probability density? And we found out that if we do some more mathematical, multiply the equation with the corresponding complex conjugate and do some more mathematical calculation, we can reach the probability density, which will be like, if I know what is the Dirac spinor, and if I take the complex conjugate, basically the Hermitian conjugate, complex conjugate, then we can find out the probability density. And this probability density, it will be always positive because it is just multiplication of two matrix, right? The complex conjugate of this one. So by definition, we get the probability density, it's supposed to be positive. This is what was expected because that's how the equation is itself defined. So that was not some surprise that we get this positive probability density because this is how the equation is itself defined. And also we can get the probability current in the vector form, which is like if I know what is a alpha matrix, and then if I take the this complex alpha times psi x with psi dagger x, then we can get the corresponding current, three vector current. Then from there we can define also the four vector current. So when we at some point we arrive at a certain conclusion that okay, from the Klein-Gordon equation we get the negative energy, negative probability density, but from the Dirac equation we can get the positive probability density, but negative energy possibility was still there.
Yeah.
Then we try to understand what is the interpretation of this negative energy, because this negative energy solution was not nullified when we try to solve Dirac equation also. To do that, what he considered, okay, we had a possibility of negative energy that come from the equation of motions, so we cannot ignore it because otherwise, until there's something wrong, we cannot ignore it. To prevent that positive energy electron making a transition to the lower level energy, so he make another postulate that whenever we consider a normal empty state, or whatever we in a normal language we call vacuum state, so he defined that there will be no positive energy electron present in the normal empty state or vacuum state. And based on that assumption, if we keep in mind the Pauli exclusion principle, then he defined this vacuum state. He considered all the negative, so all this negative energy completely filled with negative energy electrons. So there is no possibility to any electron from the upper energy level can fall to the for negative energy level or the vacuum or empty state because it's completely filled. So Dirac, to make his story in more prominent, he also included one more theory called hole theory. So he said, if there is an absence of negative energy electron in the Dirac sea, that means the possibility of all negative energy, he interpret that as a hole. So he basically introduced another particle in the system, which make the theory a bit more complicated because initially we start with a single particle theory, but depending on this or based on this whole postulation, we can reach up to the multi-particle theory. So that is a place what Feynman was not very happy with that, though at that point already the antiparticle was discovered and the Dirac theory was well established. But what was basically a concern to Feynman, that he don't like to make the theory more complicated. So he wanted a theory of this negative energy, kind of interpretation of this negative energy, in a more simpler way. So he don't want this multi-particle, because whenever in any theory there's more than one particle, the dynamics will be more complicated, because there is, if you have only one particle is moving, you can very easily try to understand the dynamics.
Yeah.
But when you have more than one particle, you have to understand the dynamics of this particle, also their interaction between each other.
Action.
So the theory will become more complicated. So
Mm.
to avoid this complicacy in the theory, basically, because anyway, I mean, any theory, when you have, suppose you are working alone at some of the project, you have full freedom to do whatever the way you can construct the project. But when you have many of them, you are doing more kind of collaboration with thousands of them. Everyone has their own opinion, so project will become more complicated.
Mm.
So what apart from this, already we discussed this one. So what Feynman considered, he considered, okay, instead of considering the whole as another particle, we can define this negative energy particle as an antiparticle, instead of
Mm.
considering a new particle like whole. But we can define in based of their energy momentum, the four energy momentum. If a particle have a positive energy, the antiparticle, a positive energy, whatever the four momentum or the four vector it will be. For antiparticle, it will be just minus of the particle. So
Yeah.
that make the theory become more simpler. What Dirac did, he introduced the idea of vacuum, which is full of all the negative energy, and also he introduced this whole theory. And also when Dirac, he tried to tackle the problem for the Klein-Gordon equation, Dirac cannot do a conclusion what Klein-Gordon got. But when
Yeah.
Feynman used his theory, based on his postulate or interpretation, he can work both with the Klein-Gordon equation and Dirac equation. So
Okay.
he can make a connect. He can play with all of them. That means he does not need to introduce the additional complication of the multi-particle. What he postulated, the negative energy particle which propagating backward in time, that will be equivalent to positive energy antiparticle propagating forward in time. So he just
Yeah.
play with the four momentum. The positive four momentum goes to negative four momentum.